Okay, welcome back, Year 12 students. Here today, back in 306. We're going to do the preparation of a standard solution. This is one of your requirements that you need to learn how to do. And today, the standard solution that we're going to be making is sodium carbonate. Okay, we're going to produce a 0.1 molar solution, and I'm going to go through the process on how to do and prepare that properly. So in the first instance, we probably need to start a calculation, and we're going to be using this analytical scale here, very, very sensitive scales, measures to about 10,000ths of a gram. Now, in the first instance, this is what we're going to be using. This is an analytical grade reagent, so it's pretty much almost 100% sodium carbonate and hydrous, so it contains no water. It has its maximum limits of impurities. These are all the impurities there. For our purposes, we're not really concerned about that. It's 99.5%, which is pretty good for a reagent. And another important thing is that we have the molecular weight here. So sodium carbonate has a molecular weight of 105.99. So the molecular weight of Na2CO3 is 105.99. That's very important. Now, to produce a 0.1 molar solution, we use the formula number of moles equals mass over the molecular weight. We want 0.1 molar solution multiplied by the molecular weight gives us the mass that we need to put into 1 litre of water or distilled water. So it's 0.1 multiplied by the molecular weight, which is 105.99, equals the mass in 1 litre. So 10.599 grams in 1 litre of H2O gives us 0.1 molar solution. Now, we're going to need only 250 mils because we're going to use a 250 ml volumetric flask. Now, this volumetric flask at 20 degrees Celsius, this one, room temperature, 20 degrees Celsius, fill it up to the line, right, the meniscus at the bottom is exactly 250 ml. That's why it's called a volumetric flask, very accurate. So we're going to prepare 250 mils of 0.1 molar sodium carbonate standard solution. The standard solution is a very, very accurate solution. Now, what we're going to do now is work out exactly how many grams we need. So if we divide this by 4, it gives us 250 ml volume. So 10.59 divided by 4, 10.599 divided by 4 equals 2.645. We'll round it up because we can only go to 3 decimal places here on our scale, so we'll do 3 decimal places. And if we look at our booklet, 2.65 is in the same order. So now what we need to do is to weigh out accurately. Now it doesn't have to be exactly 2.645 because to weigh out 10,000 of a gram is almost impossible. So what we need to do is we need an accurate figure, and then we work backwards, and we might end up with 0.11 molar solution or 0.995 molar solution. But that's what we need to know, the actual final concentration of the solution. So now, when we measure out our samples, our chemical, we put them in a wash glass. The wash glass has actually got a name, it's called a boat. So we place it in our scales, zero everything, and we know that we need to weigh about 2.645 grams, about. I've taken the cover off because it makes it a little bit easier. Okay, that's enough. Got that stabilised. So we've weighed out our sample. Weighs 2.492 grams. So now we need to transport our 2.492 grams into our volumetric flask, and this is how you do it. So we grab our watch glass. Now this is very important that we don't spill not even one or any of it at all. Okay, so we tap it into our funnel. Now it doesn't stop there. Now there's always traces left on the watch glass or on our boat, so what we do is just wash those all down. Okay, and then we get them into there. So let's get it. We'll turn away for a second.
Okay.
So we've got them here really well. Now, if you look up here, so we can see that there's traces on the side there. We need to wash all those down. Watch glass has already been done. And that's all of our chemical in the volumetric flask. Now, we need to bring that up to the marker. And the best way to do that is to pretty much pour the bulk of it in first. We should be using a funnel here, but because I'm so stable, I can do this. I'll give credit to myself for that. You generally would not do that because you can get it in your hands. Now, don't fill it right up, give it a swirl, dissolve all the solids before you go any further. Now, because we're not going to sit around for 20 minutes trying to dissolve all that, we need to get it up to the volumetric marker. So what we do is using our I might just have to get another one of these. All the squirt bottles. Bring it up to the marker. Now the bottom of the meniscus has to be in line with the marker. And don't rush this, because if you go over, you're going to have to start all over again. Alright, we're going to go really slow. Bottom of the meniscus is about there. Now that's pretty close. Now you can see here that there's a lot of bubbles happening. As the sodium carbonate dissolves, get a little bit of reaction, get a little bit of carbon dioxide being formed there, very small amounts. Also, shaking it up doesn't help. That point there will eventually drop a fraction. You come back, top it up to the marker, and that's it. Now that's your standard solution. Now that's as accurate as you're going to get it. Your scales will measure up to 10,000ths of a gram, and the accuracy is usually half the smaller scale division. So half of 10,000ths of a gram, so it's 0.00 plus or minus 5. Okay? Your teacher will discuss the errors with you. If you want to have this any more accurate than that, then you can titrate this against another acid, because this is a base. You can titrate against a known acid. But for our purposes, we don't need to go that far. That's pretty much a standard solution of sodium carbonate. And there you have it. In the next experiment, we're going to be talking about standard solutions, sodium hydroxide. And I'll talk to you about that in the next video.